Okay, so starters, have any of you guys had some experience with indoor air quality? Right? What kind of experiences have you had with it? How were you involved?
Weird odors.
Huh?
Like weird odors.
Weird odors? Okay, well, at a workplace. Okay, what kind of workplace?
Hospital.
Okay, well, hospitals are full of weird odors. That's part of their function, right? I mean, to have weird odors. And you mean like disinfectants and stuff like that, or stuff that they couldn't identify, or? Okay, good. What about, are you ever involved in situations where they're using materials, hazardous materials, and they're concerned about it getting into the air, recirculating air system or something like that? Yeah.
Where they used formalin and they thought that the fume hood wasn't working right, so they thought that they were.
Oh, okay, so people could smell the formalin in other areas and stuff like got out into the room air. Once it's out into the room air, it's mixing with everybody else's office space or lab space or something like that. And we're gonna be talking about that kind of thing. Anybody else?
Yeah, I was working a while ago in the lab. They were working with diphenylamine, which is the dishes reagent, which is carcinogenic. So everyone that was a female had to like leave the lab while.
Oh, no kidding, evacuate. Okay, and how did they spill it or did a hood?
No, it was part of the lab procedure.
Oh, I see. Okay, and that were they working it out in the open or
They
they?
didn't have any like those air vents or any fumes or anything.
Oh,
So
okay,
the
there you
smell
go.
was like getting to me.
Okay, so that was, remember we talked about engineering solution, management solutions, and that they bypassed the engineering solution, which was eliminate the hazard. They went to a management solution, which is everybody that's at risk, get out of here, right? So I guess, yeah.
That was my fault.
Okay, yes.
Filled with mold.
Oh, okay. You mean like in a residential environment, in a commercial environment? Okay, like for like inspecting it or? Oh, okay. Oh, and that's from your personal experience been an issue. Okay. Oh, good. We're gonna spend actually one or two whole sessions on mold when we come back from this exam. Okay, so that's a real hot topic nowadays, right? Okay. All right, so let's walk through this stuff. Okay, indoor air quality environment. What are we talking about? Acceptable indoor air quality environment. How do we decide what's acceptable, what's not acceptable? For starters, everybody's kind of fallback is lack of offensive odors, right? The other next part says here CO2 levels approximately the same as outdoors. That's wrong. That's not true, right? We're going to learn why that's not true in a second. We do important measurements involving CO2 levels. In fact, one of these devices right now is monitoring CO2 levels in this room. And we do it for a special reason, which you're going to be involved with now. Yes?
Carbon monoxide it's not
Well, carbon monoxide is associated with combustion, with incomplete combustion. So if you don't have something that's burning, you're not going to produce carbon monoxide, right? But almost everywhere you go, you have something that's burning, right? You got stoves, you got, and nowadays when now they have flooding in Florida, right? Flooding in Florida, a lot of people, what are they doing now for power? They're using generators. They go out and buy gasoline, propane. They're burning that fuel in order to generate electricity. The latest I heard from FEMA is that not only should you not operate a gas generator indoors, which obviously is exhausting, fumes and carbon dioxide, and so on. Not only should you not use it indoors, but it should be placed at least 20 feet from any openable window, because the fumes can drift into the house and so on and so forth, or into the trailer or wherever you're occupying. So carbon monoxide is a special issue because it's toxic. It's one of the few things on indoor air quality that could actually kill your client, right? So this instrument will also monitor carbon monoxide continuously, right? And I always monitor carbon monoxide, even if buildings in New York City, for instance, especially south of 57th Street, most of them do not have boilers. Most of them use either electric for strip heating for certain purposes, or more than that, they rely on Con Ed steam. Yeah, you ever seen steam coming out of the street and so on? Con Ed has giant turbine plants where they're producing electricity using steam turbines to spin the generators. For instance, there's one called Big Alice here in Queens. That's right by the Queensboro Bridge, the three giant smokestacks that are over there. That's the Big Alice plant. They call it Big Alice because it has three Alice Chalmers giant steam turbines in it. They burn fuel, comes out of a smokestack, that fuel. They generate steam, very high pressure steam, 750 psi steam, to spin through these turbines. Comes out of one, that's out of 250 psi, comes out another, it's down to 150, comes out another, it's 125. It's still high pressure steam. That waste steam is not strong enough, not high enough pressure to spin their turbines. So what they do, instead of discharging it, they pipe it into New York City underground, and buildings in the lower half of Manhattan use that steam as a source of heat and power. So they're heating their buildings with Con Ed's waste steam from the generating plant. Okay, they have a steam reducing valve that comes into the building. The steam goes to devices, the heat exchangers, where it makes hot water, and hot water is circulated throughout the building in radiators and convectors and air handlers, and they blow air over, and they use that to heat the building. They use it to make domestic hot water. They use it and for all sorts of purposes. So a lot of these buildings don't have boilers in them. They're using that waste steam. Though when you see steam come, usually they put, like, if it's really bad, they put like one of these cones, one of these vents, and it's coming out up high, so you're not walking through it and stuff like that. What's happening there, 99% of the time, what's happening there is groundwater, sewage, or a leak from a domestic water line is hitting the pipe. The pipe is superheated. In other words, 150 psi steam could be at like 250 degrees Fahrenheit. It's because it's under pressure, it can go above 212 degrees. So when water hits it in the street, it flashes into steam, and you see it come out of manhole covers and out of cracks in the street, and so on and so forth. So what you're seeing is groundwater or sewage hitting that steam pipe and flashing into steam and coming off the street. Every once in a while, you'll see actual Con Ed steam come out of those mains, and when that happens, you better run, because that's an explosion. We just had one, right? That just took place down by 23rd Street, right? There was a steam line explosion. Fortunately, I don't think anybody got killed this time around. The last time we had a big one was at 42nd Street by Grand Central, in front of Grand Central. It actually killed 3 or 4 people, right, when the thing exploded. As a corollary, these steam lines have been in the ground for 50, 70, 80 years. They're insulated, of course, because you want to preserve. What are they insulated with if they did it 60 years ago? Bingo. That's why they blocked off that whole section of the area there between Fifth Avenue and Madison and so on, and from 23rd or 24th down to 18th Street or something like that. Blocked off that whole area, and they had crews in there, pressure washing or hosing down all the buildings and surfaces and stuff like that to capture, and then filtering the water that they were capturing to capture the asbestos fibers. Yes? Oh, if it explodes, it happens very rarely, and that's a lot different than just the steam. The steam's venting off of it is no big problem. If you hear an explosion, that's a problem, right? Because it's under high pressure, so it can be very dangerous. Yes? Oh, okay. I'm glad you asked that, because it's going to come up here. There's a whole series of things that can cause complaints as far as indoor air is concerned. Obviously, it depends, if you're using unusual materials, if they're hazardous materials, they can generate complaints, if they cause odors and so on and so forth. In the nail salon, workers may be complaining about the odors from the nail polish or the nail polish removers and so on and so forth. In another environment might be something else. The EPA has surveyed buildings that have chronic indoor air quality problems, and they found that the single most common thing that they had in common was insufficient exchange with outside air. Because 60% of the time, that was a factor in indoor air quality complaints. Everything else, there were many, many other factors. That was the most common factor in the complaints that they got. And what does that mean? That means the air that is being supplied here in this room, that's conditioned air, is recirculated air. It's the same air that the rest of the floor is using, right? That air is recirculated through an air handler, which cools or warms that air to the right temperature, so it's comfortable in here. If they just did that over and over again, we'd smell the wipes, the odors from the wipes, the orange juice, the perfumes, the nail polishes, anything we use, magic markers, cleaning chemicals, those fumes would accumulate in that air as they're evaporated into the air, VOCs and so on and so forth. So the only way, since if we were working with these materials in a limited location, like the materials you were talking about or the formalin, we could build a hood around them and capture them so they don't get into the air. These contaminants, we can't keep them from getting into the air. So the only way we can control them is by dilution. And by dilution, we mean that as we recirculate this air, when it goes back to the air handler where the fan is, a portion of the air that's returning is dumped outside and it's replaced with fresh air. And if you don't, and what that does is it dilutes the contaminants in the rest of the air. So if you don't exchange enough air as it's recirculated, these odors can build up, right? If you are dumping enough air, you control the level of those odors and those contaminants, right? So your one way to control the accumulation of contaminants in indoor air quality is by exchanging some of the recirculated air for outside air. Or outside in New York City, we call that fresh air. In New York City, we just call it outside air. So for obvious reasons. So at any rate, so that's really part of the key of what we look for in indoor air quality issues and so on. Of course, we look for a lot of other stuff as well. It's going to be coming up. Okay, so we're looking for the design. We want to understand how the system works. That's a lot of what we're going to be talking today about, how these systems actually work. We want to talk about what comfort levels we should be keeping. Is there a standard for what's the right humidity? What's the temperature? The answer to that is yes, as we're going to say. C, there's going to be the impact of air movement. In other words, it could be the right temperature, could be the right humidity, but when the air's not moving, it can feel uncomfortable, right? You can feel that the air's stagnant. It gets to be uncomfortable. So what we're looking for is conditions where most of the occupants are comfortable and when they're not complaining, right? Why do I say that? Why don't we say that all the occupants are comfortable and not complaining? Why would I say that way? Because yes, there's another way of saying that. There's always somebody complaining. Always somebody complaining. So the objective is not to satisfy everybody, it's to satisfy almost everybody. Okay, now if it gets really bad, the EPA defines a sick building as kind of, so used to, you don't hear it so much anymore, but when this was like really first getting intensely followed in the early mid 80s and so on and so forth, there's a reason why that period is particularly at issue here. People used to read things in the paper about, sick building syndrome and so on and so forth. The EPA defines that as a building where more than 20% of the people are complaining about the indoor air quality conditions. Right? So you're not trying to satisfy everybody because you're never going to achieve that. You know that because if you're in an office, one person wants a thermostat set here, the other person wants it set somewhere else. Okay. There are standards for this stuff. The main source for standards for the way these systems operate and comfort conditions is the American Society for Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE. Okay, ASHRAE has 3 particular ones that are really directed towards indoor air quality. One of them is 52.2. Now, the years, they might have updated these a bit. That's a method for specifying filters on air conditioning systems to filter out particulate matter, dust and stuff like that. So many of you on your air conditioning system at home, like your window unit, there's like a little foam pad back there. You can hold it up, you can read a newspaper through it, right? It's not much of a filter that you're usually putting on these window units and stuff, right? It's not a very efficient filter. In large air conditioning systems in buildings, you'll typically have these like kind of 1-inch thick filters that, these blue filters, you may have seen them Sometimes I might even be able to show you some pictures now. You might have thicker filters, which are 2 inches. You might have filters that are pleated. You might have very high efficiency filters that are 8 inches thick for applications where you really want to control the dust level in a building, in a hospital, healthcare facility, in a manufacturing outfit where you're very sensitive to dust, such as pharmaceuticals or electronics or something like that. So there's a standard that defines the efficiency of filters. Okay. Then they also have something called 55, ASHRAE 55. The next part is the year. It's probably been updated since then. That's the thermal environmental conditions for human occupancy. In other words, translation, comfort standards for temperature and humidity. And that varies according to kind of facility, the kind of activities. You might want one temperature and humidity for a gym, different temperature for a humidity for a theater, different temperature and humidity for an office environment, different temperature and humidity for a conference room, and so on and so forth. So I have standards for different situations, what the comfort range should be. In general, for commercial facilities like an office or school like this, in the summertime, you want to keep between, I think it's between 74 and 78 degrees, and a relative humidity, I think, of 30 to 50% or 30 to 60%. In the wintertime, you want to keep, I think it's 66 to 72 degrees, something like that. Why do you keep a lower temperature in the wintertime? 1, 2, 3. I see at least 4 or 5 people wearing sweatshirts and jackets right now. People wear more clothes in the wintertime. You don't need it as warm. Not only that, but you're saving energy by keeping the temperature lower in the wintertime, especially if people are wearing more clothes and they don't need it anyway. In the summertime, you're wearing less clothes, so you can tolerate a higher temperature. So don't set the temperature that's 68 degrees in the summertime, because it's going to cost you a hell of a lot more energy than that range. So these are standard. The last one, ASHRAE 62, right? That I think it's up to 2017 now. Ventilation for acceptable indoor air quality. That's what we're just talking about. What percentage of the air should you exchange with outside air? That's what they mean by ventilation. The amount of air that you would exchange with outside air. The current standard for an environment like this, a classroom environment, an office environment, is that you want at least 15 to 20 cubic feet per minute of outside air exchange with inside air per person in that space. So if this floor has 100 people in it, we want 20 times that. We want 2,000 cubic feet per minute of air in the building, in this floor that's recirculated, exchanged with outside air for every minute of operation, right? So we have a standard. We have a standard that ASHRAE says if you do that, that will help control odors, it'll reduce complaints, and so on and so forth, right? Now, how do we measure that, right? Gee, how are we going to measure that? Well, we could measure, remember we had that pitot tube, and we had all these devices. We didn't really get a chance to play with them too much, but we had these devices to measure how much air was moving through vents, out of vents, through ducts, and so on and so forth. That's very tedious. If you're going to do that every time you wanted to evaluate an HVAC system, it would get very expensive to do. Not only that, a lot of this ductwork may be inaccessible. It'd be very difficult to do. So we need another mechanism to do it. In this standard, they describe research on a method that they developed for using a tracer gas to measure how much exchange you get with outside air. There's 2 ways you can use the tracer gas. One is to release a tracer gas into the air and then measure how quickly it gets diluted, right? They used to use, you don't see people doing this too much anymore. They used to use sulfur hexafluoride. Very easy to detect with a PID and or an infrared spectrophotometer, portable instrument, and you can measure how quickly the level of sulfur hexafluoride goes down. It's kind of like a Freon type gas. I don't think it's an ozone issue, but you can actually measure how quickly it goes down. Normally, they would do this, off hours to keep the air conditioning system operating during off hours. Normally, when they would shut it down, when people were not around, release it, let it kind of level out, and then set their fresh air intakes and spills and then try and measure how quickly the air is being diluted, and convert that into how many cubic feet per minute of air that must have been that you exchanged air with. That's really tedious. You got to do it at the odd hours. It's hard to control. If people are manipulating the system, like during the daytime, thermostats, dampers opening and closing, it gets very difficult to really do reliably. So what we do instead is something that's a hell of a lot simpler to accomplish. Anybody know what the CO2 levels are outside of that window? Average worldwide right now. You must be reading about this, right? Global warming and stuff. Who knows? How much? How many parts? About 400, roughly 400. What was it 70 years ago? Roughly, take a guess.
300.
Yeah, about 290, right? Just before like really main area of industrialization, it was like about 290. We're up to 400 and moving up, headed up, right? Because we're burning fossil fuels, and through burning them at a rate that's actually affecting the concentration in the atmosphere, right? So right now outside it's about 400. You know, in an area like this where you got a lot of traffic for the Trevor Bridge, if you measured it on the ground, you might measure a little bit more, 420, 450 or something like that. ASHRAE has found that the air inside this building, if it were not occupied, would be the same as outside, right? I mean, the air in here comes from outside, so the CO2 levels inside are the same as they are outside, until you screw it up and you put people into the building, right? What happens when you put people into the building? They're breathing, they're CO2 generators, right? You breathe in oxygen, you produce CO2, right? So as this air is recirculating, if there was no exchange with outside air, what's going to happen to the CO2 levels? You're going to climb, right? You're going to get drowsy. I can see it now. I must be climbing a bit now, right? Yeah, the CO2 level is going to go up and up and up and up and up. And the only way to control those CO2 levels is dilution, right? In fact, they've done research and they found that you can predict how much exchange you have with outside air by the level of CO2 that you have inside the building. So, to give you an example, if you are 700 parts per million over the outside levels, in other words, if we measure 1100 ppm in here, anything above 700 above the outside levels, above 1100 ppm, suggests you're not getting 15 CFM per person per minute inside the building. You're not exchanging enough air to meet their standard. If you're getting 800 ppm, you're well below their standard. You're getting more than you need. More. There's no such thing as more than you need. More is better in this case, because it's fresh air. The downside of that is that if it's cold outside and you dump warm air, you got to heat the air coming in, so it costs energy to exchange air. Summertime, it's cold air you're dumping out, so you have to air condition the air coming in, right? So anytime you're under that optimal level, it's costing you money in fuel, but on the other hand, it's greater comfort. A lot of indoor air quality guys will tell you don't go over 800 if you don't want a ton of complaints, even though ASHRAE says 1,000, 1,100 is still meeting their standard. Okay, so that's the key. We can use these instruments. They'll measure CO2 levels. Not only that, but they'll data log. One of them is data logging right now. They will data log. They'll take a reading every minute or every 5 minutes, whatever you program it for, store it, and then you'll be able to go back and create a chart, a graph, and it'll show you what the CO2 levels over a period of time were. Okay, so that's what we're looking at. This is OSHA, and it's on the PowerPoint. You can go through this on your own. This gives you an idea of comparison by indoor air quality guidelines from ASHRAE and so on, and the OSHA PELs and so on and so forth. The permissible exposure level for carbon dioxide is 5,000 parts per million. That's a level at which you start to maybe feel a little drowsy and so on and so forth. It's not immediately dangerous to your health, but that's OSHA's limit. It's a TLV is about the same, which kind of gives you an idea that it's probably not a real big health issue at that level. But ASHRAE's limit is about 1,000 because they're using it to control odors. These guys are just looking at it from the perspective of At what point does it start to affect your health or your performance or something like that? Carbon monoxide, ASHRAE recommends a maximum of 9 ppm. That's also roughly what I think what the maximum is in the ambient air quality standard outdoors is. But you don't want 9 ppm for certain sensitive populations, people with pulmonary circulatory problems, pulmonary problems, pregnant women, so on and so forth. Children, you don't want 9 ppm, right? That's a little bit more than you would want. The OSHA PEL for carbon monoxide is 50 ppm. Most people quote it as 35 because they've been trying to get it lowered to 35. In fact, ACGLH is 25. They've been trying to get it lowered to 35, but Congress hasn't gone along with it. It has to be published in the Federal Register. They haven't gone along with it yet. Ozone is an irritant. In other areas of the country, that's more of an issue. California, where they generate all these photochemicals from ozone and sunlight. Particulate levels, formaldehyde levels. Why do you think they brought up formaldehyde in this chart, in this summary? Why would they include formaldehyde? We're not talking about hospitals, like where we're using it as a disinfectant. Why would formaldehyde be in a house or a building? Furnishing, yeah, especially presswood and stuff like that. These artificial presswoods and stuff, and mobile homes and things like that. Especially when they're new, or if they're down south, if they're new and the sun and it's very warm and the sun's hitting them, they off-gas formaldehyde. Some insulations off-gas formaldehyde. So they have a standard for it as well, right? Why nitrogen dioxide and sulfur dioxide? Where are they coming from? They're coming from combustion products, right? Along with carbon monoxide. That might be automobile exhaust, and sulfur dioxide might be from burning fossil fuels, oils with some sulfur in them, and so on and so forth. Okay, so here again is the standards. Notice summer is a higher temperature range, and winter is a lower temperature range. Okay. Yeah, see, carbon monoxide. Look, when I did this slide, when I made this slide about 10 years ago or something like that, I was telling people it was 350. Right? It was really about 360, 370. But okay. So what happened? How did we get to this point where indoor air quality exploded in terms of concern in the very early 80s? When I was in college, they told me, when I was in college in the late 60s, I graduated about 70, 71. Depends on what you consider my graduation. But at any rate, when I was in college, they told me, I went to an engineering school. I went to Brooklyn Poly. They told me they had a metallurgy department. Metallurgy departments back in those days were largely associated with the nuclear industry because they're metals. All of these plutonium and uranium, they're metals, and so they have the science. The science for those substances are really metallurgy, in a sense. So they told me in the metallurgy department at Brooklyn Poly that by the time I turned 40, that electricity was going to be too cheap to meter because it'd all be nuclear energy. Right? Literally, it'd just be too costly to meet. It costs more to actually meter it. They'll just ignore it. The government will pay for it. They were wrong. The reason why they were wrong was because of the outfit called OPEC. They're starting to raise their ugly head again because one of the main nations in OPEC is Saudi Arabia. OPEC in the late 70s got together and they decided to reduce the amount of petroleum that they were producing. And when they did that, oil prices and gasoline prices skyrocketed. So it suddenly cost 2, 3, 4 times as much to drive a car 20 miles, to heat a building, to air condition a building, and so on and so forth. So we had an oil crisis. There was literally, I can remember, you would get on lines, you could only buy gas on alternate days. If you have an even numbered license plate, you could buy on certain days. The next day you could buy even numbered. This actually took, you guys, any of you here remember this? Yeah, one person remembers. One person's older. 2 people are old enough to remember this, right? Okay. There were gunfights at gas stations over places in line. People would camp out overnight. Okay, so that led to a real push for energy efficient design and retrofitting of HVAC systems in buildings. What did that mean? Tight buildings and efficient building. If you heat the air in a building, any of that air gets outside, you got to reheat the air you're replacing it with, or cool the air that you're replacing it with. So you want less replacement outside air. You seal up windows, you seal up buildings, and so on and so forth. Well, what happened, of course? Well, what happened is that then you wound up accumulating all these contaminants in these buildings. And not only that, but back in those days, when we put carpeting down, we used glues that were loaded with VOCs. When we painted walls in those days, we painted them with oil paints that you would smell for months afterwards, right? Take a long time it's like a half-life for these odors to come out of these materials. The furnishings were full of presswood products that contain a lot of formaldehyde and so on and so forth. So nowadays you see in most buildings, they go for low VOC paints, carpeting materials and glues that won't release a lot of VOCs and so on. Things have changed. But if you imagine a combination of those kinds of materials and tight buildings, you started to get a lot of complaints. And the term sick building syndrome became common, and it became a real problem. Okay, sick building syndrome can be a couple of things. It can be complaints about comfort and so on and so forth, but there are also building-related illnesses can be an issue as well in these issues. Okay, so for instance, one of them is Legionnaire's disease. Legionnaire's disease is associated with water that's used in cooling systems of buildings. I'm not going to get into it now. We'll talk about that separately later on. Hypersensitivity pneumonitis. That's if you use a humidifier in a building, the humidifier can grow mold, and when you spread that mold out by distributing it through the air and so on and so forth, you can get a condition which you get pneumonia-like conditions while you're in that environment. You go home for the weekend, they abate, and then you come back on Monday and you experience it again. Literally, you get fluid in your lungs, and it's literally like a kind of a form of pneumonia. Okay, a lot of people also include TB in building-related illnesses. TB really, for the most part, is transmitted person to person in close contact. But if you have very poor or no ventilation in a space, there are some studies that suggest, don't really prove it completely, suggest maybe it increases your risk. I say in a clinic or something like that, it increases your risk. So a lot of clinics are sensitive like say an HIV clinic, are sensitive to this because they have a population of patients that may be more susceptible to TB. They may have systems that give them extra ventilation, more ventilation than normal. And a lot of them you'll see use UV lights and sconces and stuff like that to deal with bacteria in the air as well. But for the most part, most people that's not a big issue in most normal kind of situations. Okay, so let's talk about how this stuff works. What you have there, right there, is your basic window unit air conditioner. How many of you guys have window unit air conditioners or something similar? So you got, but you've all seen them and stuff like that, right? You've been around them. So let's talk about how this works. If you look over here in the front, I don't know if you can see my arrow winging around there. That's a coil. You see the little elbows over here, the copper elbows over here. There's actually tubes that go straight across there. And those tubes are connected so that the tube comes across here, turns around, goes back, comes back, comes back. So it's almost like a continuous tube that's in a straight sheet for that whole front of this air conditioning unit. There's a similar coil on this other end as well. Then there's this black thing over here called a compressor, right? And meantime, we have tubing that connects all these things. Okay, I'll talk about that in a second. Let me just get a piece of paper here. Let's talk about how this works, because this is a perfect example of how almost all air conditioning systems work, because they all take advantage of the same basic principles. So a lot of times, that coil bundle was looked kind of like that. It was a straight sheet. A lot of times, most of the times, engineers kind of draw that like this as a coil, right? But it's really tubes, a series of tubes. Okay, on this side, let me just clear that up a little bit. There we go. Okay, good. On this side, right, on this side, this might be an evaporative coil. I'm going to call that evaporative coil. What does that mean? That means that there's a little valve over here, call it an expansion valve. Sometimes only a little capillary tube, but we're going to call it an expansion valve. Okay. When you're calling for air conditioning, you need cool air. That expansion valve opens up and it lets Freon liquid, right? A gas, which has this particular formula, what they call it Freon. There are many different Freons. They're chlorofluorocarbons for the most part. Nowadays, they've changed formulations a bit from just a simple chlorofluorocarbon, but it's a liquid that evaporates at a very low temperature. Evaporates at maybe 50 degrees below zero, right? Really, evaporates very quickly. Some of them even lower, right? So when you let this liquid into this coil, the Freon liquid evaporates. What happens when something evaporates? What kind of process is that? It's a cooling process. It gets cold. You pour alcohol on your hand and it evaporates, you feel cooling on your hand, right? So when the Freon is metered in liquid Freon in here, it changes from a liquid to a gas and it cools this coil, right? So what we do is we put a fan behind this coil. And this fan is pulling air in and blowing it out the front of the coil, right? Okay, so what does that do? It's cooling the air that we're blowing over that coil, right? That's your inside of your window unit. If you peel that little filter away, you see that coil, it's usually finned with aluminum to give it better heat transfer and stuff like that. But literally that fan is just taking room air, blowing it out over that coil and that filter. Sometimes it's going the other way, it blows in and blows out the bottom, but it doesn't really matter. It's blowing air across that coil and you're getting cooling. It cools the air. It cools it so much, remember it will drop temperature quite a bit, cools it so much that the condensation from the air drips down into a pan on the bottom. And sometimes that you see a tube connected to that and you'll see water dripping out the back of the unit onto the ground, right? You don't see that so much anymore. If anybody's interested, I'll tell you why you don't see it interesting anymore, so much anymore. So now you had liquid Freon, you put it in there, it evaporates, and now you have Freon gas, right? Okay, so now you got the gas, that's not any good to you anymore. You can't use it again to produce more cooling. So you need to do something to produce more cooling. So what you do is you take that Freon gas and you send it into a compressor. That's that black thing that we saw in the middle of the thing. It can be something that spins. It could be a centrifugal thing. It could be a piston, like in a reciprocating compressor, like in a car engine has a piston. It takes that gas, oops. I don't know what I did to make this smaller. There we go, okay, there we go. It takes that gas and it compresses it, right? Okay, so it's going to take that gas, it's going to compress it. Coming out of this device now, we have Freon gas compressed at high pressure, could be as much as 300 psi, right? Maybe 150 to 300 psi. It's compressed. What happens when you take a gas and compress it? If it doesn't turn back into liquid, it gets hot. Now what you have hot Freon gas. So in order to turn that back into a liquid, you have to take that heat away and it'll condense, right? So at the other end of this, you have another coil, right? And that other coil, you have a fan on it, it's blowing out, and it's cooling that coil. So as the hot Freon gas hits this coil, after it goes through that coil, you've taken the heat away and you got liquid Freon again that you can reuse to cool again. That compressor is where all the energy is. That's the thing that you hear click on, like the loud noise you hear. The fan's usually not very loud. That compressor is that loud noise that you hear that's compressing that Freon into a gas, right? So what do we have blowing out the front? We have cool air blowing out the front. If you put your hand on the other side of that window unit, you feel hot air blowing out of it, right? This process, this refrigeration process, is cooling 90% of buildings in New York City right now. There are one or two other processes they use or something, but some form of this is what's almost universally used for in air conditioning systems. You kind of have to, if you want to get into indoor air quality, you really kind of have to start to understand this. Let me ask you something. What keeps you, the air outside? Let's say the air outside is 0 degrees Fahrenheit. That's about as cold as it gets here in New York City, right? Does that mean there's no heat in the air outside? No, no, because there's plenty of heat. It goes down to, what is it, minus 454 degrees Rankine or whatever it's called, right? That's really minus 454 degrees Fahrenheit is absolute zero, right? Right. So there's plenty of heat in the air outside, right? So, let me think about something. What if I take this and turn it around? So this is the cooling coil, and this is the condensing. It's called a condensing coil, right? That's called a condensing coil because it's where the freon condenses from a hot gas to a hot liquid, right? What if I turn this around? So now the cool air is blowing outside and the hot air is blowing inside. You can use this thing to heat your house. Anybody know what we call that? Close. Think Florida. Think Florida. It's called a heat pump. Right? You ever hear the expression heat pump? That's what a heat pump is. It's an air conditioning unit that takes advantage of the air outside to pick up heat by evaporating freon. Freon absorbs the heat energy. And then by condensing it, releasing the heat indoors. And you want to know something? Just so you don't have to pick up the air conditioning window and turn it around yourself, what they do is they put valves in here. So that all you have to do is hit a button. The valves change over. So in wintertime, in the summertime, this is your evaporative coil. In your wintertime, that same coil becomes your condensing coil. That's how, when you go visit your grandma in Florida, that's how her heat pump works. Air conditioning in summertime, heat in the wintertime. Right? So that's what a heat pump is all about. Just another way of using an air conditioning system to take heat from a cold spot and move it into a warm spot. Yes. What's that? Well, Florida gets cold, and believe it or not, when my mother was alive, my parents moved down to Florida. When they were alive, it seems to me every time I was down in Florida in the wintertime, I was running out to cover a goddamn tomato plants because they were getting a frost. I'm not that serious about this, right? They gets cold down there. They need heat. A lot of people, rather because they don't want to spend the money on a heat pump, they will just put an air conditioning system in, and they'll put electric strip heating in. So, just a wire, electric, like a heater, like you would plug into a wall, like a portable heater you plug into a wall, except it's in the ductwork. Problem with that is it's much more expensive than using this kind of system to fully heat it from the outside. So if you don't have the money, it's like everything else. If you're poor and you don't have the money to spend on a $4,000 heat pump, you buy a $1,000 air conditioning unit, and then you use strip heating, which winds up costing you more than if you had bought it. Right? But you didn't have the money to invest in the more expensive equipment. Right? That's the way things are usually, right? So at any rate, it's not fair, that's for sure. So at any rate, that's how this system works. Well, that's nice, but you don't see any window units here, right? How do we get around that? How do we air condition this space here? Okay. Well, let's look at this. Let's look at perhaps for a building like this. Let's just make believe that it's this one floor. We want to cool this one floor. Well, you know what we can do? We can take a box. We're going to call it an air handler, right? We're going to define this as an air handler. And we're going to put a big coil, much bigger than the little one you got on there, but a real big coil. And we're going to evaporate freon in there. And we're going to blow air over that. And then that air, instead of just blowing out the front of it, it's going to go into a duct. And that duct then is going to go up through the ceiling, and it's going to supply offices throughout the entire floor. Right? And just as we do in here, that's going to supply all these offices. They're going to be diffusers, sometimes round ones, sometimes square ones, that are going to push cold air into the various parts of this floor. And once it pushes into the various parts of this floor, it's got to go back. So we're going to put openings in the ceiling, like back there, so that the air can go back up into the ceiling, follow the ceiling all the way back to this unit and to the suction of this fan. Okay? So the air is recirculated through this space over this evaporative coil. Now, the problem now is we have to condense that freon so it can be reused, right? And you want to know something? We'd have to have a big, well, there's two ways we could do this. We could put this against an outside wall, put another big coil in here, put another fan in here. We could do that, right? That's one of the ways that we could do that. There's other ways we can do that too. And one of the other ways that we can do that is that instead of doing that, having a lot of these units, a lot of ductwork throughout the building, what we can do is we can have a very large machine that has a cooling coil, right, an evaporative coil, and a condensing coil, right? And we can say to ourselves, rather than doing this, for every 10 offices or each side of each floor or something like that, what we're going to do? We're going to take this machine, instead of blowing air over this coil, we're going to put this coil into a shell, and we're going to run water into and out of the shell, right? So we're going to evaporate the freon inside this coil, right? And then when we're done with it, it goes to the condenser. It gets condensed and reused. There's a compressor in here as well. We're going to run water over this coil in this shell. That water is going to go in here, going to come out of here at 45 degrees Fahrenheit. Nice cold water. It's going to go to air handlers, like boxes, all over the floor, all over the building, where there'll be coils in there with a fan behind them. And instead of freon being in the coil, there'll be cold water. And then this will go back in here, and we'll put a pump on there so it's constantly recirculating. So this is called a chiller because it's producing chilled water, right? The only difference is we're using it, instead of cooling air, we're using it to cool water. Why is that a big advantage? Well, that's a big advantage because now, instead of running, a 2-foot by 4-foot duct to supply the other end of the building, now you can run a 2-inch pipe and have an air handler where then you can have ductwork locally and you don't have to have as much, and you have a coil in there you can blow air over. Well, that's great, but now you also, if we're going to do that, we're going to need to cool a lot of that. We're going to cool a lot of freon, since this is going to produce a lot of chilled water. Got to cool a lot of freon. So what you do is you put the condensing coil in another shell, and you run water over that. And you use that water to take the heat away from that condensing coil, from that freon, so you can reuse the freon. Water goes in there at 85 degrees and comes out of there at 95 degrees. It's pretty standard temperature for this stuff, right? And now it comes out of there at 95 degrees, but it's got to go in at 85 to work correctly, for these machines to work correctly. So you have to take that 95-degree water and cool it. So where do you think they put that water to cool it? Cooling tower. Goes to a cooling tower, right? What's a cooling tower look like? Okay, let's take a look at what a cooling tower does. Oops, that's not what I want. I want this. There we go. Okay, it was a cooling tower. What's a cooling tower do? Here's our evaporative coil, our chiller, right? Producing cold water. And here is our condenser. We got to get rid of the heat. There's a compressor in between, right? So we got cold water. We got hot water coming out of there at 95 degrees. We send it very frequently. It could be to a yard. It could be to a garage, wherever. Most of the time in New York City these days, it's on the roof. You send it up to the roof. You take it, you send it over to a big box. This big box has, this water comes in here at 95 degrees. It's sent up to the cooling tower. It goes into a pipe that goes across the top of the tower that splits into a spray header. It's got a whole bunch of nozzles in it. And those nozzles spray water down inside this box. At the same time that you're spraying water down inside this box, you have a big fan at the top. That fan is pulling air in from the bottom of the tower against the spray of water and out of the cooling tower. What's that do? That air that you're pulling past those droplets of water evaporates some of that water. Again, evaporation is a cooling process. So when it collects on the bottom, the sump of the cooling tower, that water is 85 degrees. So you can reuse it to cool your condenser, your Freon in that building. So if we go into these buildings, we're looking for the condenser and the chiller, which produces the cold water. The actual business of cooling or heating various parts of the building takes place in air handlers. And those air handlers have chilled water coils. Sometimes they'll have hot water coils in them as well, and fans. So then you can cool or heat the air and then send it through ducts throughout the building. And you can have these wherever you want them because you have a source of cold water. Well, but the wintertime. In the wintertime, what you do is you have another heat exchanger, a shell with a coil in it. And on that one, you're sending steam into the coil, and from, for instance, from the New York City steam or Con steam, and you're sending in cold water, and it's producing hot water, which then can go into this other coil. So in the wintertime, you can send hot water to this air handler to heat the space. In the summertime, you can send cold water to it to cool the space. Okay? So that's generally what you see in these buildings. Okay, and hopefully we'll maybe get a look at what these things actually look at, just for your own edification, just so you know. Okay, if you guys have ever seen a split system, okay, split system, the compressor and the condenser are outside, and the only thing that's inside the house is the cooling coil, the Freon coil, and a little fan. What's the advantage of that? What keeps you up at night, the fan or the compressor? Compressor, right? Compressor's outside the house. It's quiet, dead silent, right? So, so you have this is nice because you don't have to have the noise from the compressor as well. Usually they're mounted high up on a wall, so that use a. If you have a central air conditioning system in a home, for instance, you'll have a box. You have your compressor and your condenser outside. Freon tubes come in. And there's a coil. Usually they're kind of like in a little A-frame kind of arrangement. There's a coil so that air from the house is pulled in and blown past that coil. It goes up and it supplies the diffusers throughout the house and then comes back down again and gets reused. Sometimes you'll have a furnace in here as well with a heat exchanger. So you can burn gas in there, heat up the heat exchanger, and on the other side of the heat exchanger, you can warm the room air. So you can have hot air or cold air if you want. So this is another form of a split unit. Condenser and cooling coil outside, and the evaporative coil, which does cooling inside. Okay, here's another kind of look at it as well. You can see there's little burners in there and stuff. Okay, so in a big building, here's an example where you would have on the roof, maybe a 3 or 4 story building. You might see these. These are called package units. And you would have a device on the roof that has a cooling coil and a heating coil, right? And has a fan, and it has a ductwork system. It has risers. It sends air, supply air down into a space, and then across the space with the fuse. It supplies air across the space, and then on the return, it pulls air back into the unit again so it can be recirculated. But then it's got dampers in it, so they can manipulate the dampers so that return air, a certain amount of it is forced outside. And then another damper opens up, and that means as the fan is sucking air and pushing it down here, it sucks outside air in here as well. So you can match the amount that you dump to the amount that you pull in. So this version will give you exchange with outside air. Okay, we're gonna, like I said, I want to get you guys real looks at what these devices look like. This is kind of like what a cooling tower looks like. And we'll get better looks at this as well. Okay, here's another system here where here's a boiler and there's a chiller, right? There's 2 big tubes. One tube is the condenser, one tube is the evaporator, right? It's making chilled water. That chilled water is being piped to an air handler on this floor, air handler on this floor, air handler on this floor. And then the ductwork distributes the cold or warm air to these various locations. You see there's something called a terminal unit here. That is sometimes that's called a VAV, or variable air volume box. And I'll talk about that in a second. This place, they got a boiler to produce warm water that goes to these coils instead of cold at certain times of the year. They can get pretty dirty, right? Yes. Yes. The inside here, the inside air. Let me go back there. Yeah, this is the outside air intake, right? So here's your fan. Your fan is pulling air. This is the return air. Your fan is pulling air in here, right? This is under suction. And it's pulling air in here. It's pulling it across the filters, then across the cooling coil, the heating coil, and then back down into the building, right? Well, there are dampers in here, like Venetian blinds, like things to block air. They can block the airflow here. Say maybe they block it 50%. And there's a damper on here on this side, which is closer to the fan. So what happens is that it's easier for the fan to pull in outside air than it is to pull in this return air. So you can balance those dampers so that you can get 10% of the air being dumped out. See, this is where it's getting dumped outside. You can get 10% of it dumped out and replaced with fresh air. You can get 20, 30, 40%, even 100%. If they close this and open this completely, then the air can't come back into the fan. So the air is pulling just outside air, distributing it through the building, and then on the return end, it just dumps outside because the damper's closed. So that's called 100% outside air. And some buildings do this in the springtime and in the fall, so they don't have to pay for cooling or heating, right? Because they can condition it. They get, if it's a right temperature outside, they can just pull in 100% outside air and not run the air conditioning system. Just continuously pull outside air. Anybody else in the hospital business there know where you might use 100% outside air system? What's that? In the hospital, yeah. How about where you do what do you call it? Colonoscopies, right? We do colonoscopies. What do they do when they do colonoscopies? They have a camera, and what else besides a camera is in that tube? They push air into that tube. They blow air into your intestines to expand them so they can see. And where's that air go? It comes back out where it came in, right? So you can imagine there's a lot of particulate going around. You know what I mean by particulate, right? So in most places that do that kind of work, there's another name for it, with an A, can't think of it. Endoscopy suites. In endoscopy suites, you almost always have 100% outside air. And the air is directed so that all of the workers are on one side of it and they push the air through, and then it goes out, it's filtered on the way out. So it's 100% outside air. And a lot of times, since they have to be heated and cooled, it's very expensive to run those things, but then they certainly charge enough for that, don't they? So, all right. So I tell you what, let's take a break for just 5 minutes, not a long break, because I want us to play with an instrument that we have here.
This
Okay,
conference will now be recorded.
Let's see if that's working. Yep, it's working. Okay. 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 Okay, so here's another view of a much more complicated building, and more air handlers and so on and so forth, more terminal units or air handlers and so on and so forth. Here's another building with an elaborate duct system. You can see the air handler. This on the rooftop. These are units on the rooftop, and they downfeed ductwork. These risers, and they supply several floors in the building, and so on and so forth. So there's a lot of these strategies. They're all linear because the air is always moving one direction, coming back the other direction. So we're going to be learning a little bit more later on about how to diagnose this. There's many different kinds of filters, filter sizes. The filters, more efficient they are, the more resistant to flow they are, quicker they get dirty. So there's a trade-off. You can't just tell the guy, hey, let's put in really expensive, really, good HEPA filters here, because then all of a sudden you may not be getting the airflow that you need. Yes.
Do they remove micro?
No, HEPA filters, you might be getting down to the point where you might be removing some microbes, maybe not viruses though. You might need almost an absolute filter to take out a virus. So, I don't know how successful you'd be with that. Although there are systems where they use virtually absolute filters because you have places where they produce microprocessors and stuff like that, where there can't be any dust, any particles in the air at all. So there might be some filtration, but on a regular basis, no, you're not filtering down to a small enough particle size to remove filters, even with HEPA most likely. Okay, HU air handling units. Okay, the other thing is that some of these systems are what they call constant volume systems, and others are variable air volume systems. That's important. Let's presume for a moment that the air is coming in there and it's returning to the machine by those big square diffusers in the back there. These two small ones are supplying air. It sounds like I hear air blowing in. That's going back up into the ceiling and then back to the unit. Okay, there's two ways that could be working. One is the simplest system you're going to come across, which is probably about 70% of air conditioning systems. It's a constant volume system. As long as the AC is working, it's sending the same number of cubic feet per minute into this space all the time. Let's say that the air handler services the north end of this floor. Then there's a single thermostat somewhere in the hallway, just like at your house, that determines what the temperature is, and it's going to send air in here, cold air in here, to satisfy that one thermostat. So some offices might get a little cold, some will get a little warm, and you adjust that by adjusting how much air is coming out of that diffuser, right? It's nice, but there's a lot of times when it's not going to work that well as far as temperature is concerned. For example, if the zone that we're in here, one end of the building is in the sun and the other end of the building is in the shade. Well, one of us is going to be hot, the other is going to be cold. Can't satisfy both of us at the same time, different heat loads. So constant volume system, which again is most systems are constant volume systems, especially smaller systems, smaller buildings, constant volume systems. That has some disadvantages. One advantage is that that the same amount of air is being distributed all the time. So if you got the fresh air intake set right and the dump set right, the spill set right, that you're getting the right amount of exchange with outside air. And that's true because it's always doing the same thing all the time. And you can set it so that it's working right. The other kind of system you have, which is what we have here, is called a variable air volume system. And in that system, these terminal units that you see here, the boxes that you see there, might be what you call variable air volume boxes. So this ductwork is connected to a box with a damper in it. By damper, I mean like a thing that'll cut off the airflow. Like it either folds up or folds down in the ductwork, or looks kind of like Venetian blinds or something like that, something to restrict the airflow. It's connected to a device like that. Okay, the thermostat in this room controls that device. So even if it's cold outside and they need cold air conditioning, if the temperature is right here, the thermostat senses it, and that damper closes off and sends less air in here. Because we don't need more cold air, we need less. Well, since we're sending less cold air in here, we're getting less exchange with outside air. The air gets staler in here. So variable air volume systems are a little bit more problematic about getting the right amount of air exchange in different spaces, but they're much better in terms of comfort conditions, temperature, humidity, because each individual room or each pair of offices or something like that has its own thermostat. And the dampers, the air is being circulated all the time through the main ducts, but it only goes to the diffusers when it's needed. Yes?
Have something to measure the CO2.
We're gonna do that right. We're gonna do that right now. Okay, we're gonna do that in a second. The other thing that comes up a lot is humidifiers. Humidifiers are an issue. There's typically two kinds of humidifiers. One kind of humidifier is a device that takes that takes a reservoir of water and heats it up, so it evaporates water into the air. Problem with that is that you can grow stuff in that, and minerals can build up in it, and so on and so forth. Another time, we'll take actual air, take actual water and spray it into the ductwork. Another kind will take steam and spray it into the ductwork in order to produce moisture. Most buildings like this do not bother to humidify the air. That's why in the wintertime, you get chapped lips in these buildings. You have to wear contact lenses. It's irritating and so on and so forth, because the humidity in these buildings can, the relative humidity outside is relatively low anyway. When you take that cold air and heat it up, you have air with very little moisture in it. When you heat it up, it has the capacity to hold more moisture. So the relative humidity goes down as you heat the air up. So it makes the air seem very dry. So very few buildings actually bother to humidify these days. The ones that do usually are the ones that have big data centers. Because when you know what happens when you have low humidity in the wintertime, you rub your feet on the carpet, well, you get static, right? So they can't stand the static. Printers can't stand the static, but because of paper handling issues, right? And for instance, a museum or something like that would have valuable artwork or something like that. You have to continuously control the humidity very carefully to protect the artwork and the materials and so on and so forth. But in ordinary schools and office buildings and stuff like that, these days they don't put the energy into humidifying. Plus, humidifiers are always problematic in terms of they're not working right. You don't keep them clean. You don't maintain them. Then you could be spraying water in there. It can condense somewhere and start growing some mold and stuff like that. Okay, so let me just go through this quickly. Single most common factor in indoor air quality in sick building issues is insufficient exchange with outside air. How can we measure that? We can measure that by measuring the CO2 levels. And as it happens, we have devices they're made by a company called TSI, and they're called AQ5, these are called AQ7545s, IAQ Calc. This device has sensors in this probe. They usually have a thing where you can just mount them on a desk or something like that. You can just wave them around, I guess, right? This device has sensors in it. It has sensor for carbon dioxide, for temperature, for humidity, and for carbon monoxide. And it has a display in which you can display three. You can tell it which of those three you want it to display. It's measuring all four, but you can tell it to display. Right now, it's displaying CO2. It's displaying relative humidity, and it's displaying carbon monoxide. The others might be displaying temperature. I'm not sure, but this data logging this particular one is data logging all of those things. Okay, so before we started in this classroom, I didn't show it to you, but the reading on here was I think it was somewhere about 540 parts per million of CO2. Can you see what it's reading now? It's reading basically 898, 900, right? Why is it higher now? You guys weren't here. Only 2 or 3 people here when I first brought these things in here, right? So it's actually, the relative humidity, only 19%. It's below the comfort level, right? We're not going to deal with that because it costs too much money to deal with that, because too many other issues, maintenance-wise, and so on and so forth. We tolerate the low temperature, the low humidity here, unless there's a good reason to try and humidify and so on. Okay, and right now it's reading 0.4 ppm of CO, carbon monoxide. Where's that coming from? Coming from the street. There is a boiler. I think there might be a boiler in this building. I don't know if it's operating now, but we're probably not getting any CO from that. But we're getting it from the street. If you went down to the street, you'd probably be reading 1 or 2 ppm. Why is it lower in here? Elevation. We're off the street. Right? As a matter of fact, actually, it's lower in here because the air handler, which is really supplying us with air, is really on the roof of this building, which is, I think, the 12th or 14th floor or something like that. So it's 140 feet off the street. So it's down to 0.4 ppm CO, carbon monoxide, right? Where down at the street, it might be 1 or 2 ppm right now. On a really busy day, traffic backed up, trucks back, honking, fire engines going by and stuff like that, you might get a few ppm more, maybe 3 or 4 ppm or so. National Ambient Air Quality Standard, what was it? I think it was 7 or 9 ppm or something like that. Once you get above that level, You have to report it to the EPA. How do they know it's above that level? They put test stations all over the city, monitoring the air. They move them around different places, and they take readings. They have to report to the EPA to let them know. So we have 3 of these instruments. Okay, so I'm going to suggest that, for instance, if you want to divide up into groups of 5, right? We're going to leave this one here. 2 groups of 5 will take, each will take an instrument, go somewhere interesting, measure the CO2 levels, compare it to this room, right? And then come back. Go for about 5 minutes, test a few places, maybe out on the street, see what the levels you get out on the street, and so on and so forth. Or maybe go into IT, bother them in IT, and it takes a little while for this to equilibrate, so you might want to, just give it a minute. You'll see the number will change. Give it a minute until you see it's kind of leveled out, and record where you are and what the levels were so we can compare them. Maybe you can find a really crowded classroom and sneak in and wave it around and get a reading, right? Okay, get a reading. Now, just so you know, keep it away from your face, because what's going to happen if you put it in front of your face? What's going to happen to that CO2 level? See you going up. Okay, 1100. That's going down quickly because I took it away. All right, but yeah, take 2 groups of 5. Pick one of these instruments up. Take a walk. Come back in 5 or 10 minutes, and then the next group, 2 groups of 5. Okay. Yes. Okay, so these IAQ monitors, this IAQ, it kind of latches on there, make it a little easier. These IAQ monitors, right? These are kind of the primary thing that an indoor air quality investigator would use. This is one of his main tools, because this will give him a lot of basic stuff, give him comfort conditions and so on and so forth. You might, as you go around, see if the comfort conditions change also. See if the humidity, this one's showing humidity instead of temperature. I can change that. Let me see, I won't change this one. Whoa, look out. This one is showing, what is it showing? Oh, it's showing temperature, good. This one's showing temperature and humidity. Okay, that's good. Temperature and humidity and carbon dioxide. Temperature and humidity and carbon dioxide, okay. Hey, other group, next group. Hey, I'm not gonna hold the gun to your head, okay? I'm not going to hold the gun to your head, but I only have 2 other instruments. This one I'm running in here so we can connect it to your computer. What's that?
We're just looking at the CO.
You want to look at CO?
No, yeah, that's what we're looking at, right?
All right, that's carbon dioxide.
Yeah.
Okay, hang on a second. Yeah, and that's relative humidity and temperature. I'm going to change it to CO. If you go down to the street, see if it's a little bit higher.
Okay.
But you guys are going outside?
I guess.
Okay,
They're going outside.
They're right out. Oh, okay. They're going outside.
We're gonna go outside.
They're going outside.
All right.
Where do you go? Right in front of the
Where
Oh,
you guys are going then?
I had to write that.
building? I'm gonna.
They are.
Oh,
They're going over there.
CO, got it.
Where are you guys?
Temperature, I'm going to turn that one off.
Reading room?
Ah,
Are we going outside?
Anybody could go. They're going
I know.
outside. Yeah, we're gonna go outside.
I'm just
I
thinking.
know that. Come
Alright,
on,
I'm
let
going
me see
outside
it.
with them then. I'll see how you guys think.
Relative humidity.
Yeah.
Off. I gotta turn it off.
It is
Yeah, how do I-
freezing.
ah.
Shoot.
Relative humidity.
Really?
I think you have to
I
turn
like
off
the
one.
cold, but not like.
Yeah, I'm
soup.
trying to turn it off. Change is not safe. Okay.
I'd rather put on wine.
I don't know what key to push to turn it off. Relative humidity.
Off is this one.
Oh, okay. Oh, yeah, there it is. It's right there. Okay, good. And CO2 is on? Yeah, so you'll have 3. Okay, good.
Smokers.
Good, there you go. That one's displaying CO now. So if you go down to the street, you might actually see some level.
CO2, right? Wait,
That's
CO is the bottom.
CO2 and that's CO, yeah.
Gotcha.
Alright, so I'll go with you guys.
Okay. Okay, this one I'm hanging on to. And there's a reason why I'm hanging on to that. Okay, where's the power button?
Being recorded, right?
See, we got lucky. Okay, 7:36.
This is only the spring.
Mission completed.
Okay, what'd you see?
The higher we went up to the 14th, no,
Yeah.
13th floor, and the parts per million decreased.
On the CO2 levels?
Yeah.
Okay, because those floors, probably nobody hanging around there anymore. Yeah, fewer people. Because remember, it's all mixed.
Also went outside actually.
What was the level outside?
Yeah,
400,
decreased actually.
400,
Oh,
almost 500.
470, 480.
Yeah, okay, there you go. And the only reason it's above 400 is because probably from the autos and stuff like that. I mean, worldwide, I think it's around 400, 410 now. We're not really representative of the rest of the world necessarily. But hey, come on. Okay, so if some of you guys want to give it a try, take the instrument, take a run outside, or go, take a run around the building. Or at least pick up the instrument and check it out. Just don't take the one I'm using. Huh? I don't mean check it out. I mean, look at it. Leave this one here. This one I want to use for something. I'm going to use for something.
Yeah, breathe on it.
Oh, it went
way up, yeah. Hey, honey. Nah. Let's get 1,000. Can we get 1,000 now? Oh, man. It's coming down real slow. 69, 70. Oh, yeah. CO. How do you see the CO? How do you see the carbon monoxide level?
It'll only show you 3 of the 4 readings at one time.
Okay.
So you have to go into display, press enter, or press the middle button, the menu.
Right.
Middle button menu. Go to display, hit enter on display.
Oh, menu you said? Menu? You said menu?
Menu and then display.
Display setup?
Display setup.
Okay.
And now you can tell it which ones of those you want to turn on to show on the display.
I see.
You can only show 3, so if you're gonna change it, you gotta turn one off.
What do you want? The CO is on. That's I guess you got. Escape. There you go. CO. Oh, there you go. What is it? CO. 2. All right. That's good. Interesting.
So how does it work now?
Right now, it's reading the CO2 level is reading 990, 980, and so on.
Okay.
That is the relative humidity, and that's the parts per million of carbon monoxide.
Okay.
I'm not sure that that's calibrated perfectly well. I think it's a little lower than that. And basically, if you want, this is the menu.
Okay.
You can go in there and you can change the display settings. So let's say you wanted to display temperature instead of temperature. You want to turn that on. You can turn that on, right? But the only problem is you can only display so many at a time. So yes, I'm going to go down and turn off relative humidity. Off. So now it's going to display temperature instead.
And they all are displayed at the same time.
Those 3 are going to display, but it's monitoring, it's downloading and monitoring all of those at the same time. See, now it's displaying temperature and carbon monoxide. And you could leave this out instead. This one right now, this one is,
Yeah, it's going up.
this one.
Went up to like 800 and something.
Yeah.
CO2.
Yeah, I can always tell, if I leave them in an office, I can tell when there's a big spike in the CO2, and one of the people in the office is singing like Strangers in the Night or something like that into the microphone. See, and this one right now is data logging. Every minute it's taking a CO2 reading, temperature, humidity, and carbon monoxide reading and storing it. And then you can connect it to another computer and you can download that data and graph it or get a summary of it.
How much do these cost?
Probably about 1,000 to 2,000. So about 2,000, probably closer to 2,000, but at least 1,000. And then you need a kit. You also need a kit to calibrate them. There's a sleeve that's over this, and you get a cylinder with 1,000 ppm CO2 and 50 ppm carbon monoxide, and you flood it. And you make sure that it's reading that. You can actually recalibrate it as well.
And the calibrator doesn't come with it?
The tube comes. The tube that you put over comes with it, but the cylinder and the regulator and all that kind of stuff doesn't come with it. Those you buy separately. Yeah. Yes. So what'd you see that was, take a seat. We'll talk about what you might have seen that was interesting. And unfortunately, the software, I can't believe the software. How is that even possible?
The numbers? That's CO2.
Carbon
Well, Wingstop was 725. Not 775. Well, I think the curve 725. But outside. It was less, it was like 5 something. Okay, I just don't know. Very-
Okay.
Just be fast.
Okay, guys, I just want to show you quickly what this looks like when you take these instruments and you download this information. First, so for instance, here's a graph that was produced from another instrument, similar instrument, and you can see at the top we have a graph of the CO2 levels, we have the temperature, and we have the relative humidity. On the bottom you see carbon monoxide, but the levels were so low that they were always under 1 ppm. So there's a little bit blue line down there. It pops up a little bit every once in a while, but it's kind of hard to see. Is that displaying behind me? That is displaying behind me, right? Okay, so that's, if you want to get a closer look, I'll show you what the CO2 levels look like. So this would be connected to a Windows computer. You download it, and then you can ask it to display, and you can tell it what channels you want to display, if you want just CO2 and so on and so forth. Oh, you're not supposed to see the address here, so ignore the address. But what can you tell me about this particular facility? Look at the CO2 levels. What can you tell me about this? Yeah, well, first of all, number one, what's happening here? This is across 4 days. So what's happening is they're going way down at night, right, when there's nobody around, and the highest levels are midday, usually like afternoon, mid-afternoon or something like that. What are the highest levels here? Are they over 1100? So what would you say about this particular facility? Not necessarily. There could be nobody complaining, right? But what we can say is that they're not meeting the ASHRAE standard for ventilation with outside air, exchange with outside air, right? And this could contribute to indoor air quality problems. Here's one that summarizes temperature and humidity. So you can either plot these forward to a page, or you can just plot the individual ones. And notice that as the temperature goes up, what happens to the relative humidity? Goes down. Relative humidity, temperature goes, and so on and so forth. They're related, right? The warmer the air is, the more capacity it has to hold moisture. So the relative humidity goes down. As you cool the air, it goes up until the air is so cool that the air can't hold it. You haven't added any moisture. What happens at night, overnight, right? The air gets cool. You go out to your car in the morning, right? And the amount of moisture in the air hasn't changed. The temperature has. The temperature has dropped so much, it's gotten to a point where the air could hold that moisture and be like 50% humidity during the daytime. At night, it's cold. The cold air can't hold as much moisture, and you reach the dew point, and the water from the air condenses out onto your car. So you find that dew on the grass, on the car, or whatever in the morning. Because relative humidity means relative for that temperature, relative to how much moisture the air could hold. So when you say air is 50% relative humidity, you don't know how much moisture is in the air. You only know it's at 50% of what the air could be holding at that temperature. Without knowing the temperature, you don't actually know how many milligrams of water per cubic foot are really there. You just know it's half of what the level should be, what the level could be, maximum 100% humidity, right? So that's what they define as relative humidity. So when you design humidifiers and stuff, it's important to understand that kind of stuff. So I just want to finish up with a couple more slides. Okay, so one of the things you want to do is you want to measure this flow rate. This device here you use to hold up over diffusers to make measurements. These are various kinds of indoor air quality monitors, such as this Iaq monitor that we're just looking at. And again, this gives you a good idea. You could set this up In an area where people are complaining, you could determine the ventilation rates, you could check the temperature over a period of time. Remember, if you just go in there and wave this thing around, all you know is what the conditions are at that moment, right? They may not be the same the whole time that, like the whole time that person is there. And, they're going to tell you that, well, it was different an hour ago, right? So now you have a look at what the comfort conditions are, temperature, humidity, what the CO2 levels are, the ventilation rates. So in other words, if we had taken, remember that chart I just showed you? If we had taken the CO2 levels at 9 o'clock in the morning, we might have said you got enough ventilation in here. But it hadn't had a chance to build up yet. You didn't have as many people there as you would have in mid-afternoon. Some people out in the field running around and so on and so forth. So getting that picture over a period of time, data log, getting that picture over a period of time helps you out. For specific compounds, you can use a photoionization detector, as we talked about. You can use infrared measuring devices. You could use these sorbent badges, Draeger tubes. You could use this canister, which is evacuated. You fill it with air from the space, send it to a lab. They send it to a GC or mass spec. The dust, you can use optical devices to measure dust levels, as we did with the I think the P-Trax and so on and so forth. We'll do this kind of analysis, gravimetric, and so on and so forth. Mold, we're going to talk about mold completely separately when we come back next week. That's going to be one of our labs. We're going to actually take home Petri dishes and leave them open for 20 minutes in various areas of the house, and then close them up and grow some mold and bring them back in. Right? We're going to play around with that. We don't have the best way to do this, which would be to like take mold spore counts, and all of us have 27 pumps. But I could come up with at least 3 Petri dishes for everybody, so they can try a good place outdoors and a nasty place to see if we get a difference in your home or your apartment or something like that in terms of levels. If we want to actively sample mold in the air, we would use these spore traps on the left, or we use a Petri dish with this thing called an Anderson sampler on the right. I'll have one here to show you what it looks like. Okay, smoking, other important issues. Smoking, nowadays smoking is not allowed, but remember, people in condos and stuff like that, they complain, my neighbor's smoking, get them to stop, because the fumes, the smell of the smoke come, wind up finding pipe chases, ways to get into other apartments. As far as other issues and air quality issues that produce health effects, asthmas can be infected by dust mite, frasses, crap from dust mites, roaches, pet dander, and so on and so forth, Legionnaire's disease associated with water systems. The EPA has something called an environmental relative moldiness index. They have a device you can send the waveform. You can connect it to it's a filter basically, connects to a standard vacuum cleaner. It tells you to measure off a certain area in the busy part of your house, vacuum that area, and send it back to them, and they would tell you whether your house on a percentile basis has more mold or less mold than other homes in the country. It's kind of a rough, weird kind of measurement, but they actually still do this. So you can actually, Draeger tubes, you can test CO2 levels with them. You can test hundreds of other, contaminants that might be present in a specific area where you're using an unusual material as well. Okay, so I think that's enough for tonight. Okay, so this is your primary tool. Indoor air quality, have a lot of other tools that you use sometimes. This one you use all the time.